So please.
Thank you very much for the presentation, and thanks again, Christina, for the invitation too. I'm happy to be here, and yeah, I will talk to you about some models and algorithms to deal with the high-dimensional setting, and as well when the data are distributed. My interest in this subject is about mainly to deal with heterogeneous data, which may be often unlabeled, and we say we are in an unsupervised setting, and this data can be also high-dimensional and potentially distributed, typically in large-scale settings. And the scientific challenge we can I will focus mainly on how to design sparse models while keeping in mind their interpretability, and to make them scale to a large-scale data settings. And also we have another objective in mind, which is to deal with privacy issues, typically to not share individual data. And as it was just mentioned, my research part is mainly on statistics. So I have in mind this question about dealing with uncertainty quantification. And sometimes we need to also integrate some prior knowledge, which can typically come from physics, but it can also come from the structure of these data themselves, even if we are not dealing with a physical problem. And maybe more formally, the subject of the presentation today is about latent variable models. We suppose that, for example, if we observe some data X, and this observation is just a marginal observation of a more general phenomenon in which there is some variable or some data Z, but these data are not necessarily directly available. And for example, in the parametric setting, we need to infer this distribution from only the observed data, while of course taking into account that there is a hidden variable Z. Typically, if you know about clustering problems, for example, these variable Z can represent the clustering structure, which is hidden. For example, in the case of classification, we do not know necessarily the classes of all the observed data. And so the topic is mainly about unsupervised learning, and also especially in the high-dimensional setting, some of main approaches in state-of-the-art try to not account for all the variables that we design for the data. So the idea is just to try to design what we call sparse models around a subset of these variables, while keeping quite enough performant model in terms of prediction, for example, if we are doing prediction. And also selection today, I will talk about it in another sense. If we are dealing with the clustering, one question is, for example, how many clusters in the data? So in this setting, we will not select subsets of variables, but we will select a subset of models with different number of clusters. And the approach these approaches will be mainly built upon statistical background. So don't expect too much machine learning talk. And why this focus and this attraction to this kind of statistical or probabilistic models is namely because we can also have formal guarantees on both approximation capabilities and also learning capabilities of these models. And as I said before, we can I will talk a little bit also about how we can regularize these techniques, for example, to deal with the high-dimensional setting, but also this can join other problems we typically deal with in SystemX, which is about scientific machine learning, or generically called hybridization. I will also talk about federated learning, which is one way to deal with what is now called the trustworthiness. Okay. Here is some parts I expect to talk about. I will first introduce a family of models called the mixture of experts, which is a way to deal with heterogeneous data, and then how to adapt them to the high-dimensional setting. The high-dimensional setting is typically the case where when you have too much of variables compared to the number of observations. But I also talk about another setting in which we observe typically a time series as a variable. So this is the third part here, and how to deal with model and variable selection in this setting. And the other part is about federated learning, where when the data, for example, are by construction distributed, or when we need to distribute them for some sense, typically to scale up the computations, so how to deal with the learning of these models. And the objective is also to make sure that these models can be statistically justified. We have some good statistical properties, and also from the algorithmic point of view, the algorithms that we construct to learn these models are efficient in terms of, for example, computing time, but not just in terms of that. They should typically operate in an unsupervised way, the case in which you do not have necessarily access to the classes if you do classification. Let's make sure that the concepts are clear to all of us. To recall that when we talk about the high-dimensional setting, we suppose that we observe some variable x here of dimension p, and the high-dimensional setting means that we are potentially have a number of variables p that is larger than the number of observations, and we can look to a further dimension of this high-dimensional setting. It is the one in which each variable is a function itself. For example, in case of time series, you can have some variables that are continuously recorded during time, and then you have some x of t, and t is the time, and it's considering that it is just simply a vector, it can be in some situation limiting. And the idea is how to construct some kind of light models and to keep them interpretable, especially from the user point of view. I just give here two practical examples. For the functional predictors, you can, if you can see here, for example, we are interested in predicting the precipitation in some region here. And these regions, for example, do not necessarily enjoy the same weather properties. So there is a kind of heterogeneity, which is at the end, in terms of statistical modeling, can be translated as a clustering problem. And you need to deal with that given these time series. So here we have typically a functional predictor, and the time series here are, for example, during the year, what was the mean temperature, okay? So here you observe some variable y, which is the precipitation at some location, for example, and the predictor is x of t, t is time, and x is the temperature. And similarly, but in another setting, in radiology, for example, you can observe this kind of images, and the idea is to segment the image to, at the end, detect if there is some cancer, some regions that present a kind of cancer. And some techniques in radiologies use this kind of physical modeling, and here the input is based on the energy on some energy values. So here, for each pixel in the image, okay, we observe a curve like that. So typically, in terms of learning modeling, we observe some y here, which is the pixel in 3D, for example, and for each y, we have a curve x of t. T here is the energy value in electron volt. Okay. What is challenging in this setting? For example, if you have homogeneous curves of in simpler situation like that, you can do simple functional linear regression. This is a state of the art. But if you need to predict in this functional setting, while taking into account clustering properties here for the y, for example, here in the image, all the region of the image are not supposed to respond the same thing given the input of this energy input. So you need to go further to deal with this heterogeneity. So roughly speaking, a simple model is not enough. The idea is to use a collection of these simple models, okay, which we call a mixture of models. And typically here, one interesting setting is what we call the mixture of experts. I think they are now very well popularized with generative AI. But the principle is a little bit old, and it supposes that if you see, for example, here in this situation, some input X and you need to predict some output Y, okay, you suppose that a simple linear model, for example, is not enough, but given this situation, you can mobilize many of these simpler models, okay? And so the idea here is for each subset of the data, you will fit what we call an expert, so it is a simpler model, okay? And you take the responses of all these experts and you combine them in some way. The way here, we call it the gating network. It is simply attributing a weight to each response, and then you take this aggregation, this weighted response, as the final output, okay? And as you can see here, the continuous line here is the final aggregated mixture of expert model. At the same time, what is interesting in this kind of modeling, you can get a kind of unsupervised decomposition of these data. You look to each subset. You can look to each subset of this data as a cluster, so as a potentially local different behavior in your data, and it is then up to you to interpret later in terms from, for example, an application point of view to what this would correspond, okay? And here, for this picture, it is the density of this mixture of experts, okay? What is interesting in this modeling is the fact that you can adjust them, you can play with them to your need. And what is typically used is a mixture of Gaussian experts. You take each simpler model as a Gaussian distribution. In the context of regression, you will take, for example, linear regression with a Gaussian noise. But if you expect that your data are not, for example, necessarily symmetric, they do not exhibit the same tails like the Gaussian, you have some noisy points in your data, then you can extend and you can use what is available actually in the probabilistic literature. Rather than using, for example, a Gaussian expert, you can use a non-symmetric Gaussian expert, you can use a student T expert, and here what I show to you, it is the student T expert that has, additionally to the Gaussian model, for the Gaussian distribution, I suppose everyone knows that we have two parameters, the means and the standard deviation or the variance. And for this QT, which is the skewed T distribution, for the T distribution, you have an additional parameter here, which is new and represents the degrees of freedom. And the lambda is an additional parameter to account for the potential skewness within the data. Okay, and here I show you some examples. Here it is a mixture of two normal experts, in the sense two Gaussian experts. Here two Gaussian asymmetric experts. You can see that there is no necessarily symmetry here. So the lambda varies. Here you have two student experts, and here you have two skew student experts. And then, according to the value of your lambda and if you're new here, you can recover simpler models. For example, when the number of parameters of degree of freedom goes to infinity, and when your skewness parameter lambda goes to 0, then you recover the Gaussian case, yes.
Just to know, the skewness you are talking about, is it the statistical skewness?
Absolutely,
okay.
Yes. Yeah.
And I do not understand lambda. Lambda key.
Lambda is it is a parameter of the skew normal distribution. The skew normal distribution, it is the normal distribution, if I can say, plus an additional parameter account for skewness. Here, for example, you see this is
Is it redundant, the two?
No. Okay. Look, the lambda here is specifically related to the skewness. Here you can see this mode is not symmetric. Okay, but the new here accounts for the tails for this part. Okay, yeah. And so the point is, you can use mixture of experts with the Gaussian distribution. It is one first way to deal with this heterogeneity, and this allows you to capture, like here, clusters within the data and to predict, in the sense that to capture the model here. Okay, you attain two objectives. If this is not enough because you have some, for example, let me show you this example. If you put some outliers here, okay, or you put them here, and then you adjust the mixture of Gaussian experts, and then the adjusted red curve is not clearly enough, because the ground truth here is the continuous black line. But if you use, for example, here student T, and then you clearly accommodate better the outliers here. And similarly for this, it is a real data set, but it is really too simple. So the question here, it is a flexible modeling, but of course it is still on small data. But there is still a question. Here we suppose that the model is given, the parameters are available. So how to adjust them to the data, how to learn them? There is a popular algorithm in this setting. We call it the expectation maximization algorithm. And the idea is we start by the fact that it's not directly possible to maximize the likelihood, but we can use the AM algorithm to maximize it. The idea is quite simple, but of course it is very clever. We artificially complete the data with these missing data, Z. That means you take your pen and you write your likelihood by supposing that these Z's are as available. So what we get here is much more easy to optimize. But since this is not the objective we need to optimize at the origin, and then there is the second, there is the hint of the EM, we maximize the expectation of this log likelihood that suppose the missing data are available, conditionally on the observed data. You always have in your hands the observed data, and a current value of the parameters. And when I say the current value of parameters, that means you do it iteratively, okay? So you iterate the E and the M step until convergence, and there is a result that says that you converge to at least your local optimum of the log likelihood, okay? And we share these some codes on the on GitHub if you wish to get to look to that, okay? Please feel free to ask if there is a question. This part, yes, please. Yeah.
Your data leaves some in Euclidean space. And what about doing clustering just based on distance without introducing a parametric model with this class of, say, mixture of Gaussian or mixture of... So I'm just trying in high dimension, particularly, I mean...
Yeah. Actually, until now, they don't yet speak about how to deal in the high dimension. But at least later, I will mention two cases. The first case is traditionally, we assume that it is an existing Euclidean space, and we regularize about the parameters. But there is one setting, I hope it will fit to your question. If these data are supposed to live in a functional space, so we do approximation. If you remember the picture in which there is these curves, this kind of time series, if you assume that they arise from functions, and this is what we do, but the function, it is something that lives in an finite space. Cannot in practice work on that. So what we do typically, we take these functions, this time series, and we fit a B-spline model to them. The B-spline is, I can say something in the middle. It's not purely a vectorial modeling. It's not formally a functional modeling, but it is something in the sense that you project your functions on a finite number of basis functions. Yeah, so, but outside of this setting, I do not talk about that here, but there is some work on like graph, kind of graph data or graph related data in which the space is not necessarily simply an Euclidean space. Yeah.
But so the more global question was, I mean, in these cases where you are in Euclidean spaces, I mean, what is the reason for introducing parametric model? Whereas you could do clustering just based on the pairwise distance between all.
Yeah.
So that was my question.
I see more, and thank you. For at least two reasons. The first reason is that, and I will just talk about that right now. With this, in this parametric setting, we have a formal characterization about their approximation capabilities. Within this parametric family, we know for such setting that we can approximate up to an arbitrary error the model. And the other point is that always within this parametric setting, we can have also guarantees on prediction. And I will just talk about this now. But of course, there is always these parametric models versus purely distance-based models, like I suppose k-means or things similar. So yeah, I am personally attracted by this kind of modeling, at least for these two features. Thank you, very interesting. So as I just said, for this kind of models, actually mixture of experts, you can see at them as an extension of mixture models. And if we go back to these mixture models, where the difference is simply that this one, if you take your observation xi that live in some space D, and you need to approximate the unknown density f to do later, for example, clustering, And if you consider this approximation within the class of finite mixture models, precisely finite location scale mixture models, which can be defined like that, you have the finite mixture H of K mixture components with kernel or with mixture, with component distribution phi, which is a sum, weighted sum with some weights pi k that are positive and sum to 1. And D is the standard deviation for the case. And the location, the location parameter is mu, and the scale is sigma. This is a mixture distribution. It's not a mixture of experts, but they are both quite similar. The difference is, I will show you to that later for mixture of experts. So if you work with this distribution, which is a parametric, okay, we have this universal approximation capability. If you take any probability density function f, n1, you need to only take a kernel or a component density phi that is continuous and built open a compact set. The Gaussian is included in this family. Then you are sure that there is a sequence of mixture models of number of components k that converges to the true density in the supremum sense. Okay. So otherwise said, you need to take as more as a number of components as you can to get a better approximation. Okay. And you can, if for p more than 1, if your density f, the target density f, you need to approximate is a density of Lebesgue, and if phi is, there is another hypothesis on it, if it is an essentially bounded PDF, again, essentially bounded PDF, the Gaussian is one of them. Essentially bounded, that means that the measure of your density is 0 outside the support of its compact support here. And then you get quite more interesting result. Then you have this convergence in the Lebesgue sense. Roughly speaking, you consider this parametric density, and if you have, if you put more number of components, and then you have a stronger approximation result. Okay. And I was just, I just mentioned it for the mixture of expert case. The main difference is that the weights here also depend on the inputs. Okay, this is the main difference without speaking too much about math here. That means now for the mixture of experts, we are doing prediction. We have the notion of the input X and the output Y, and these output and input are related by the conditional density now. We are in a conditional density setting f of Y given X. We need to approximate it. And then in the I dimension on both the input and the output, if we consider the family of mixture of experts, which is a finite sum about some weight here, that itself depends on the input and some kernel here, it can be Gaussian or another thing. And then if you consider the mixture of experts where the gates are built on a softmax, I think this is a very traditional choice. Mixture of experts with this gating network is a softmax. Okay, if you take this setting and then open some quite simple hypothesis, then typically if you take this conditional density you need to approximate that is continuous, and you take a kernel that is also continuous, if you can renormalize your data to make them in 0, 1, and then the sequence of mixture of experts converges to the true density in the Lebesgue sense. We can even get a stronger result, but for for one dimension, in one dimension. So there is the convergence result here is in terms of almost uniformly convergence. This is to say Of course, we can limit ourselves by working with parametric models, but to balance that, we have interesting approximation capabilities. And yeah, again, how to learn with these models? We still using the EM algorithm, which is the same setting. We try to maximize the observed data log likelihood. We cannot do that because this log of sum is not quite friendly. We use the EM to handle that, and simple to code and to practice. Nothing especially special to mention in practice, unless, of course, it is like any most of the EM algorithm, you do not necessarily have the global convergence, but still you have the guarantee to converge to at least one local optimum of the observed data log likelihood. Okay. Yeah, just some application for time series. I just talked about this application. Something may be interesting for to mention. Yeah, we can actually, this was an extension of these models. We can deal with other kind of variables here with the spectrograms, time frequency representation. And what is interesting here for this example, these were the sound signals of marine mammals. And the idea in that project was for biologists to try to understand how do these marine mammals do communicate, if potentially they have some kind of vocabulary. Or so at the end, from a statistical point of view, we have clearly here a structure in the sense of clusters, number of segments, but their number is not necessarily known, including by biologists. And you run in totally unsupervised way this kind of EM algorithm for mixture models. You obtain this kind of segmentation, and you clearly here for these quite interesting parts of the signals, which are not noise, this vocalization, clearly identify them. For these less vocalizing parts of the signal, you also identify them. And for the rest, it should be something like a noise, okay? To focus on the example I showed about radiology and the image segmentation to detect cancer parts. The model here was adapted in a simple way. We suppose that each observation here in the image, for example, in a 3D, you call it, for example, Y here, the value of the pixel at some location. We observe these X's. The coordinates of these X are important because an image is by construction, by nature, a spatial information. The spatial information is very important. And for this, sorry, V here is the spatial information, and X here are these curves of energy. So in the ideal case, normally each region here in the image would have its corresponding cluster here within the curves. But of course, this is a very real situation. And if you observe it like that, you cannot necessarily identify, for example, the region of interest here. But if you take a mixture model in which you suppose that the weights are related to the spatial information in the image, and the responses are these functional output. This is a kind of softmax, and then you can see here. This is the annotation, the ground truth, and this is the clustering. And the red one is quite well identified. This was done in partnership with people from McGill and including radiologists. And just to mention that simple models like that can work for some situation. Of course, I'm not sure that people in radiology do use too much such simple statistical models. The question of the reviewers was always compare with deep learning, etc. And I think it is very relevant. But here it is a balance between the quality of results, the simplicity of models, and their interpretability. The same thing here I'm mentioning. I'll go a little bit fast on this part, but to mention here, as I introduced it, one question is how many clusters in the data, okay? What would be the best solution? This one, etc. Of course, according to the criterion we built is, can see it is this one. So to do selection, including variable selection and model selection, you can regularize this kind of models. You are, I suppose, familiar with the lasso, which is the L1 regularization of a standard linear regression model. But here it is a mixture of many models, of K models. So if you penalize them with L1 and you have a regularization like that, one acts for the experts network and the other one acts for the gating network, okay? So the message here is you can still regularize, but the setting is not the same like in the standard lasso, in the sense that you will not have closed form solutions for the parameters. You still need to use the EM, but there is no strong issues. At each step, you need to estimate a subset of the parameters here, of the beta and of W, according to the weights that the E-step gives to the E-step. For those who are familiar with the EM algorithm, it is the step that mainly gives you the posterior memberships of the data to your clusters, okay? We do it in some way that is efficient. Just here to mention, the regularization can also concern for multidimensional experts. If you use the Gaussian model, then you will have a covariance matrix. If you are in high dimensional setting, we can focus on sub-blocks of this matrix, okay? And we have a way to identify these block diagonal, to identify block diagonal structure, okay? And for this part, sorry, I still have maybe 5 minutes or, yeah.
So do I get it correctly that now in this setting, you what you call clustering is identifying subsets,
yeah,
and matching or finding, say, a Gaussian or whatever distribution, high dimensional for each subset, and your mixture would be the combination of those. That's what you mean?
Yeah.
Okay, thanks.
Yeah, absolutely, yes. Yeah. And additionally to what I mentioned before, behind this selection, we have an interesting result. I will not talk too much about that, but this result just says our way of regularizing, if we add this penalty here about the model, if we are able to correctly adjust this penalty, and then the expected loss of our estimator is comparable to the oracle, to the loss of the true model, up to some multiplicative constant. And this is for any value of n. So it is not only available asymptotically. So it is a non-asymptotic result. Okay. So here we have this penalty. If we can adjust it, and we have a way to adjust it that is proposed by Pascal Massart and the colleagues from Paris-Saclay. We call it, this is, I mean, a standard technique that is used in this setting. And it is the heuristic de pente, heuristic. Sorry. Slope heuristic. Thank you. Yeah, it is the slope heuristic. And now I just just would like to take the remaining time for the other part. Sorry, don't have. For federated learning, I suppose everyone is familiar here to at least what my colleague Francesca told me about. Federated learning here, in my understanding, I consider the case in which there is some clients that infer locally some model, and there is an orchestration at the central server. So I consider the federated learning in the centralized setting. So the main questions here: how to make sure that at the central level we have an estimation, a quality of model that is comparable to those estimated locally, while ensuring that there is no need to share the data themselves. We can only share the parameters, okay? What we did here, if locally we think that a mixture model is interesting for our task, and then we locally fit the mixture model. There is one model here for client 1, another model for client 2, etc. And we have FM for client M. And then we send these models to the central level, and there is an aggregation here. So the question is how to aggregate locally. Of course, one simpler way, if we have F hat M for any client coming from client M, we can take the average. This is a very good density approximation. If you need to approximate the density F, this is a very good estimator. But if you need to keep this interpretability in terms of clustering, and then we have an issue here, since that with F bar, that is the average, we do not have directly interpretation of K clusters, but there is K clusters, M, or M, the number of nodes of machines, of clients, etc. And our idea is, rather than using directly this mean estimator, we will use another one that is we call it a reduced estimator, and this estimator is constructed in the follow according to this construction. We take this aggregation, you see it, that is the mean estimator, and we look to the closest mixture model to this mean estimation by minimizing a divergence, typically a Kullback-Leibler divergence. This is just to make sure that we have a good density estimator aggregated according to the average sense. But since this is not interpretable in terms of K components, it enjoys M times K components, we target a distribution HK that has by construction a K components, and we minimize the divergence between both, and typically Kullback-Leibler divergence. Okay, and this estimator is consistent if we are able to locally construct consistent estimators. Maybe one last. Of course, this is just results to say that we compared with other competitors, and it works quite well. We can also aggregate quite recent deep learning architectures, LSTM with dynamically spatiotemporal graph recurrent neural networks for urban mobility setting. And we added a client-side validation. Locally, you learn your local model, you share it with the central server, and then you get back the aggregated estimator, and you have in your hand locally a validation set. You calculate the validation loss with the model returned from the central server. If the validation loss is improved, then you take it. If not, you keep your own model. Okay. And we applied this on urban mobility. Here are the data. Urban mobility. This work is done with people from Gustave Eiffel and from Lyon. They have data from Orange, estimated from phones about origin destination matrices, about multimodal transportation. And also for the same setting, they are estimates from the local authorities in high-speed roads, etc. And the idea is how to make sure that both can collaborate to estimate correctly these origin destination matrices without sharing their own data. And we use this kind of modeling, and in the results, you can see here, the estimations are quite okay. The paper is still under first revision. So, but we think it is enough interesting to be shared to the community. Here, for example, you can see that in the red, the the client-side validation loss allows to improve a little bit the loss. And they can answer the question. I will stop here. Thank you for your attention, and sorry if I took too much time.
Could you say on the last part a few words on the algorithmic aspect? I mean, if I remember well, there was this Kullback-Leibler divergence, and you had to compute some closest point in this K mixture, and so I mean. Is it implementable? I mean,
yeah, we implemented it. It is implementable. We implemented it, but we also received the criticism mentioning that actually to minimize this transportation loss from here to here, each is a mixture distribution. At some step, we do not have other choice than sampling. So sampling, by definition, can take some time. But yeah, it works. It is. We implemented it for this data, but it's not maybe necessarily something that is obvious in the sense. It's not built open closed form solution. This is what I can mention.
But how do you determine the closest point in this very complex space?
There
is an algorithm for that? Or?
Yeah. Okay. Formally, if you define your row here, if your row is the Kullback-Leibler divergence, you have here this. It is computed. This, for example, a mixture of Gaussian distribution of m times k components. You have the values of the theta, that means the beta and the sigma, etc. And for hk, it is a mixture of the same model, but with a different number of components. So again, you have the analytic form of the model, and you calculate the Kullback-Leibler divergence. You get some expression. This expression is not for some kind of mixtures, is not closed form. So to get it, you need to do some sampling. So at the end, yes, you calculate it, but with a complexity that is different. For example, if this model here is the simpler model, is not a mixture, of course, the computation will be much more easy.
Okay, but to get the if there is a gradient of some kind, or I mean.
Yeah. We use actually, it's not a gradient descent. We use a minorization algorithm, an MMM algorithm. Actually, here, behind that there is an MMM algorithm. It's not. I think in some settings, I mean, more generally, it can correspond to a gradient setting. Not sure, but at least I know if MMM in some setting, it can recover the EM algorithm. But here, yeah, it is an MMM algorithm. We construct some majorizer of the function and we minimize it, etc.
Thank you.
So in the federated learning setting, even if you don't transmit the data, you transmit model parameters. And there are some attacks, such as membership inference, that permits to know whether a particular data sample was used for the training of the model. So when you use a mixture of expert strategies, is it better or worse with respect to such attacks?
Thank you very much. Very interesting questions. Just to maybe clarify, the notion of attack and was not at all treated here. By privacy preserving, it should be limited to the fact that we only share the parameters, not the data. But still, as you said, of course, and I know some of our colleagues at least at SystemX worked about this aspect. I believe that considering a kind of I don't know a GAN architecture in addition to that would be interesting, but we do not yet look to the attack neither attack construction nor attack defense in this context of mixture experts, but definitely it is very I mean it is an issue. Thank you.
Questions?
A distance.
Question online? So thank you again.
Thank you for all. Thank you for those connected remotely.